Now once you see this, that means I'm going to start already. Now this part here, good morning. Now this part here we are doing gas turbine power cycle. Okay, the gas turbine power cycle, and then this is an open unit gas turbine. Okay, open unit gas turbine or open gas turbine unit. And then of course I will show you the closed gas turbine unit as well. So now from here, you can see in this diagram here, you can see that, okay, you have basically in this open gas turbine unit, you have three devices. Okay, the first one is the compressor, the second one is the combustion chamber, and the third one is the gas turbine. So you don't have any cooler or any device for the heat reject. Okay, usually what they do is, okay, it is straight away exhaust to the atmosphere. So you can see at the outlet of the gas turbine, you can see is hot gas. Usually they just discharge this, theoretically they discharge it to the atmosphere, but then this is no good because it will create air pollution, okay, or global warming effect. So now this is a gas turbine power cycle open unit, and it follows a constant pressure cycle. So that means it is similar to what we have studied in your constant pressure cycle. The only thing that, okay, you don't have 4 going back to 1, because at point 1 here, it is usually the air that is taken into the compressor is fresh air from the atmosphere, and then the outlet or the exit of the gas turbine is in the form of gas, so hot gas. So you cannot mix the hot gas, or you cannot redirect the hot gas back into the compressor instead of fresh air. So now from state point 1 to state point 2, okay, we say the air will undergo an isentropic compression process. Isentropic compression process, that is air. State point 1 to 2 is air. Then point 2 you have compressed air. So when the compressed air goes into the combustion chamber, it undergoes a burning process. And then you have constant pressure heat supply from state point 2 to 3. But as a result of burning and chemical reaction, okay, so the exit that is at point 3, it has become gas. It's not pure air, or it is not air anymore. So for that heat supply, constant pressure heat supply, we have to consider that stream as gas, not air. For air is 1 to 2, and for gas is 2 to 3. So from 2 to 3 onwards is gas, hot gas. So then from state point 3 to 4, it undergoes an isentropic expansion through the gas turbine, and where a certain amount of energy or work has been extracted from the hot gas in order to drive, okay, propellers, or to drive a generator, or etc. etc. So the discharge as hot gas. So usually the gas turbine open unit, you have a combined system, usually combined with your steam power plant, okay, in order to form a combined heat and power unit. Okay, so in the notes it says that fresh air at ambient condition is drawn. Okay, hold on for a moment. So fresh air at ambient condition is drawn into the compressor. So going into the compressor is fresh air, where its temperature and pressure are raised. So pressure and temperature are raised in the compressor because it undergo a compression process, that is isentropic compression theoretically. Okay, so the high pressure air proceeds into the combustion chamber. This is your combustion chamber, okay, where the fuel is burned at constant pressure. The resulting high temperature gases then enter the turbine. So where it undergoes isentropic expansion, where they expand to the atmospheric pressure while producing power. Now the exhaust gases leaving the turbine are thrown out, not recirculated, okay, not recirculated, causing the cycle to be classified as an open cycle. So this is an open constant pressure cycle. Okay, so state point 1 to 2. Now you can see the notes below here. Okay, so state point 1 to 2, that is isentropic compression. Then state point 2 to 3, that is constant pressure heat addition. And then you have state point 3 to 4, that is your isentropic expansion. Remember, you don't have heat rejection here. Okay, you don't need to calculate heat rejection. So based on this, your net work output, you have to calculate based on the work output from the turbine minus the work input in the compressor, from the compressor. So now this is your TS diagram. This is a TS diagram, okay, for your gas turbine unit, your air open gas turbine unit. So this is a constant pressure cycle. This is a constant pressure cycle. So as you can see, normal constant pressure cycle is from state point 1 to 2, then from state point 2 to 3, then from state point 3 to 4. That is a usual constant pressure cycle, then from 4 back to 1 on the TS diagram. Okay, so now, but if you were to refer to an actual or a real gas turbine unit, okay, for the compressor part and the turbine part in this case, we are not looking at the combustion chamber yet. We are only looking at the compressor and the turbine. So it is known that we know that state point 1 to 2 is actually your isentropic compression process. So in real practice, okay, there is no perfect isentropic. That means no perfect heat loss, no perfect energy loss due to heat to the surrounding or internally. But it is actually, or in real life, you have a certain amount of energy loss and it becomes irreversible. So it is irreversibility. So the actual or the real gas turbine cycle, usually it is from state point 1 to 2 prime. That is your actual flow path. Okay, we no longer follow state point 1 to 2. So state point 1 to 2, we therefore can categorize it as a theoretical work input. 1 to 2 as a theoretical work input. And then 1 to 2 prime as the actual work input. So now, based on this theoretical work input and actual work input, we can define what we call the isentropic efficiency for the compressor. Okay, so when you say efficiency, usually is less than 100%. So therefore, okay, the numerator, okay, we will choose the theoretical work input, that is T2 minus T1. The theoretical work input is, now here is A, so you have CPA T2 minus T1, and for the actual is actually CPA T2 prime minus T1, where T2 prime is the actual temperature at the compressor exit outlet. So point 1 is usually your A intake temperature, usually is of the atmospheric A temperature. And then isentropic compression, that is to point 2, that is theoretically. For the actual, you have to take 1 to 2 prime. Okay, so 1 to 2 prime is irreversible. So if let's say the question has given us the isentropic efficiency for the compressor, and let's say we can obtain T2 by using the temperature pressure relationship for isentropic that is shown here. Okay, you can find out your T2 with both the pressure or the pressure ratio, and with the gamma, that is the adiabatic index for A, and that is usually taken as 1.4. So therefore, you can calculate T2 here. Then after calculating T2, then you will be able to find out the T2 prime if you know the isentropic efficiency for the compressor. Then from 2 prime to 3, that is your constant pressure heat addition in the combustion chamber, and that is the combustion temperature, and this temperature usually is referred to as the maximum temperature in the cycle. Then if let's say when the hot gas expand isentropically, if it expand isentropically, or let's say we say perfect isentropic, then you have 0.3 to 4. Perfect isentropic means you have no heat loss, no energy loss due to heat. Okay, so but that is theoretically, but in actual cases, definitely the actual work output that is produced by the turbine is less than the theoretical work output by the turbine. So again here you have another term that is called the isentropic efficiency for the turbine is defined. Earlier was the compressor, so it's denoted here C, and here is denoted as T. So that means we are referring to the turbine. So again, efficiency is usually less than 100, less than 1. So the numerator, the number of the numerator should be usually smaller than the denominator. So therefore, we take the theoretical work output, the actual work output, which is smaller, the value or the magnitude should be lower as compared to the theoretical work output. So we have actual work output over theoretical work output to give you the isentropic efficiency for the turbine. So this is isentropic efficiency for compressor, theoretical work in over actual work in. For turbine, you have actual work out over theoretical work out. So if question has given us the turbine, the isentropic efficiency for the turbine, and from this we know T3, let's say the maximum temperature, we use this formula, we can find out the T4. But the gamma here is different. It's not A anymore, because 3 to 4 and especially 2 prime to 3, you have to consider that as gas. So the heat supply here should be Cp subscript G T3 minus T2 prime. The G means it is referring to gas. So the specific heat capacity of constant pressure for gas. For 1 to 2 prime is for A. So your work input should be Cpa T2 prime minus T1. Your heat supply should be Cpg T3 minus T2 prime. And then your actual work output should be Cpg T3 minus T4 prime. That is your actual work output. So the Cpg or the Cp for gas or the gamma for gas usually is given in the question. So no problem. So you can substitute your gamma for gas to find out in order to find out your T4. Once you have found out your T4 and with the isentropic efficiency of the turbine, you can find out T4 prime. So once you have done with all the temperatures, then you can calculate the work out, the work in, and the heat supply, and the efficiency as well. So I'll just roughly read out the notes that is written here. The deviation of actual gas turbine cycles from the idealized, that means the theoretical ones or the ideal ones. The actual gas turbine cycle differs from the ideal ones due to 1. Some pressure drop during heat addition, that means 2 prime to 3. In actual case, you have pressure drop. Usually you have pressure drop in the pipelines. So therefore, okay, based on this, okay, it is still theoretical. It's not the actual process yet. Okay, not the actual process yet. Okay. So the actual work input to the compressor, that means 1 to 2 prime here, is more, and the actual work output from the turbine is less. Okay. Now the actual work input is more here, and the actual work output is less here. Okay, from the turbine is less because of the irreversibilities. because of irreversibilities. By now you should know what is irreversible and reversible, okay? So the deviation of the actual compressor and turbine behavior from the ideal ones, okay, behavior can be accurately encountered by utilizing the isentropic efficiencies for the turbine and the compressor. So you must know the definition, at least know the definition of the isentropic efficiency for compressor and for the turbine, okay? So this is based on your steady flow energy equation. So we can work out every each part here, okay? So you can work out the work output, okay, in the turbine. So remember, you see here, this is CPG, not CPA as what you used to write every time. And then this is T4 prime, not T4. Okay? Then for the A side, that is the compressor. For the gas side, that is the gas turbine. And this is the A compressor. So again, you can apply steady flow. So neglect whatever it is not so important or negligible. So you have the work input as this. So this is CPA, can you see? So that is usually standardized as 1.005. And this is T2 prime and not T2, yeah? So this is in the combustion chamber. So the combustion chamber also we will take CPG. Okay? So you have CPG here. Remember, usually students, okay, misconsider this value here. They treat everything as A 1.005 unless that is a closed gas turbine unit. Unless it is a closed gas turbine unit with 100% perfect isentropic. With 100% perfect isentropic, okay, 100% perfect isentropic, and then closed cycle, then this will become CPA. Okay, then you can consider this as CPA. If it is an open unit where you have A going in, gas coming out, then this should be G, subscript G. Okay, so that is your net work out. That is how you calculate your net work out, your work in, your heat supply, your cycle efficiency, the work ratio. Now the work ratio here is the net work out, that is your work out minus work in, over the gross work expansion. So the gross work expansion here is only the turbine. It's only the turbine. You don't consider the heat supply part. Even though if let's say you refer to PV diagram, yes, there is an expansion, but we don't refer to that. We only refer to the turbine work output for the gross work expansion. The net work out, you can no longer take heat supply minus heat rejected unless it is a closed gas turbine unit. Open gas turbine unit, okay, you can take work out minus work in. Okay, so that is for your power. Okay, to calculate the net power output, first thing you must have the mass flow rate of air. Sometimes questions might give you net power output, and then you found out the work output, the net work output, then the question will ask you to find the mass flow rate sometimes. So this is your closed gas turbine unit. This is the same, actually the same as your constant pressure cycle. So the open gas turbine unit is actually the modification of your closed gas turbine unit. Okay, so it's actually the modification. Now you see here, this part here is, okay, I didn't draw any dark blue line here. That means it stops here 0.4. Or if you consider actual case, it should be here 4 prime. Okay, so this is open gas turbine unit. Okay, and this is your closed gas turbine unit. Okay, so you can see 4 prime back to 1. So this line here is a solid line now. And then you have heat rejected. Okay, and here you have your heat supply. And then here you have your actual work out. Okay, unless if isentropic efficiency is given, then you have this dashed line or this dashed line here. If the question say perfect isentropic, or if the question doesn't mention anything about isentropic efficiency, Usually we take this as a straight vertical line to point 2, no 2 prime, or this vertical line here from 3 to 4, so you don't have to show the 4 prime. If it is a closed gas turbine unit and without the isentropic efficiency, or if they consider perfect isentropic, then you shouldn't show 3, 4 prime and 1 to 2 prime. Okay? Okay, so that's all basically. So this is the quiz. Is that a quiz? Okay, so you have your tutorials here. So thank you very much. And then we will continue with the tutorial in the next lesson. Okay, so you still have a part 2, yeah? But then we are